Imagine peering into a nano-sized racetrack and asking, could an electron act like one of those catalytic nanomotors, zipping straight ahead, looping in circles, or spiraling in a 3D helix? And if it could, might that help us understand why electrons sometimes behave like particles and other times like waves? How do we power an electron? With a nanomotor, you dump in chemicals, say hydrogen peroxide, and the motor breaks it down to push itself forward. Electrons have no enzymes or catalysts, but they do carry charge, so their fuel is simply electric and magnetic fields. Apply a voltage, an electric field, and an electron accelerates in a straight line. Insert a magnetic field perpendicular to its motion, and the electron curves into a circle or helix because the Lorentz force keeps tugging it sideways as it moves forward. In essence, the fuel is electromagnetic potential energy, not molecules. What motions can electrons exhibit? Straight, when only an electric field is present. Circular, when a static magnetic field is perpendicular to velocity. Think of electrons spinning in a cyclotron. Helical, if there's both an electric push along the field lines and a perpendicular magnetic pull, tracing corkscrew paths through space. So yes, you can steer electrons into straight, circular, or helical tracks just by cleverly arranging fields, much like setting the rails for a motor car on a track. But there's no catalytic surface or chemical reaction at play, just forces acting on a charged particle. Can this explain wave-particle duality? Here's where the analogy breaks down. Nanomotors always behave like tiny machines. You know precisely when and where they go, subject to some Brownian wobble. Electrons, by contrast, obey quantum rules. They have a wavelength, the de Broglie wavelength, that depends on their momentum, and in experiments like the double split, they produce interference patterns exactly like waves. No arrangement of fields or fuel can turn a purely mechanical driver into a quantum wave. Wave-particle duality isn't about how fast or how far an electron moves. It's baked into the fabric of quantum mechanics itself. So, what have we learned? Electrons can indeed be driven in straight, circular, or helical paths. Just swap chemical fuel for electric and magnetic fields. Their trajectories mimic those of tiny motors on microfluidic tracks, but without any catalysts or substrates. Their mysterious wave behavior, however, isn't a byproduct of propulsion. It arises from their quantum nature, entirely separate from the forces that bend their paths. Understanding electrons as field-driven nanovehicles is a fun metaphor, but it won't demystify wave-particle duality. That deeper mystery lives in the equations of quantum mechanics, not in the little motors we build for chemical fuels. Electrons are often modeled as point particles, yet quantum field theory and Dirac's relativistic equation suggest they possess internal dynamical features. The concept of Zitterbewegung, German for trembling motion, describes rapid oscillatory motion due to interference between particle and antiparticle components. This motion is confined to scales near the Compton wavelength and may be undetectable directly, but still physically meaningful. Such internal fluctuations could result in structured paths that generate wave-like behavior. Rather than passive carriers of charge, electrons may continuously move in subtle, high-frequency loops or spirals. The Dirac equation predicts a trembling motion of electrons at nearly the speed of light, even in a vacuum, pointing to non-classical internal structure. Like a hummingbird's wings that blur into invisibility while hovering, the electron's rapid internal motion may generate observable quantum effects. Catalytic nanomotors operate by converting chemical energy into mechanical motion using surface reactions and field gradients. These systems often rely on asymmetry in geometry or reactivity to produce directional motion without external driving. They can move in straight lines, spiral trajectories, or exhibit orbital rotation depending on symmetry and boundary conditions. Their propulsion arises from local interactions at interfaces, particularly from diffusiophoretic or self-electrophoretic mechanisms. Studying these behaviors offers a model for how charged particles like electrons might self-propel in quantum fields, Janus nanoparticles, asymmetrically coated with catalytic material, can convert hydrogen peroxide into propulsion, creating straight or curved trajectory, like a spinning firework rocket that curves or spirals due to uneven thrust. Nanomotors move based on where reactions occur. If electrons exhibit tightly wound helical or rotating motion beneath quantum resolution, this could give rise to their observed wave-like interference patterns. Their probability distribution may be a macroscopic projection of deterministic but rapidly oscillating microtrajectories. The apparent superposition of paths in experiments like the double slit may reflect the geometry of internal motion rather than true duality. This idea bridges quantum behavior with classical motion through geometric dynamics. Such models challenge the Copenhagen interpretation and point toward deeper substructure in particle behavior. In electron interference experiments, single particles produce fringe patterns, even when fired one at a time, hinting at hidden deterministic pathways. It's like a dancer twirling while walking forward. The path may look smeared or wave-like, but it results from intricate movement. The quantum vacuum is not empty. It is filled with transient fluctuations of fields and virtual particles. These fluctuations can impart measurable forces, such as in the Casimir effect or the Lamb shift. If electrons couple dynamically with these zero-point fields, they may extract energy to sustain internal motion. This would serve as a fuel source without requiring mass exchange or traditional chemical input. The vacuum would act as a universal background engine, potentially driving all subatomic dynamics. Electrons in orbitals experience tiny shifts in energy levels. Lamb shift due to their interaction with quantum vacuum fields. It's like surfing invisible ocean waves. Although unseen, the energy in the water's motion propels the surfer forward. Spin is traditionally treated as an intrinsic, non-spatial quantum property with no classical analog. However, if the electron traces a helical path at relativistic speed, this could create effective angular momentum. This internal circulation could generate magnetic moments consistent with observed spin behavior. The spin quantization would then emerge from stable modes of this motion under boundary conditions. This reinterprets spin not as a fundamental mystery, but as a geometric result of structured motion. The electron's magnetic moment is slightly greater than the Dirac value, suggesting hidden complexity in its motion. It's like a ball rolling forward while spinning on a spiral track. Its overall effect mimics a built-in spin. The de Broglie hypothesis states that particles have associated wavelengths inversely proportional to momentum. If electrons follow circular or spiral trajectories, the projection of their path could define a wavelength matching this relationship. This would allow matter waves to arise from internal orbital motion rather than being abstract wave functions. Standing wave conditions could then explain quantization of energy levels naturally. It recasts wave behavior as an emergent spatial phenomenon, not a probabilistic abstraction. Electrons confined in atoms exhibit standing wave patterns that determine their allowed energy states. It's like a slinky spinning as it moves. Its coil spacing sets a natural wavelength that influences its motion. Even if electrons are internally self-propelled, their paths can still be altered by external fields like magnetic and vector potentials. The Aharonov-Bohm effect demonstrates that electrons react to potentials even in field-free zones. This suggests that external influences modulate phase or trajectory without adding energy. Such phase-dependent steering mirrors how nanomotors are directed using electric fields or gradients. Electrons may thus be navigators in a quantum field landscape, rather than passive responders. In field-free regions, electrons still shift their interference fringes when exposed to enclosed magnetic flux. It's like a bird adjusting its path due to a subtle change in wind pressure, not because it was pushed, but because it sensed the potential. Pilot wave theories propose that particles follow real paths guided by a surrounding wave field. Experiments with droplets on vibrating liquid surfaces mimic this behavior. Each droplet generates a standing wave and follows it. These macroscopic systems demonstrate tunneling, quantization, and even double-split interference. The implication is that internal propulsion, coupled to wave guidance, can reproduce quantum-like behavior. This strengthens the idea that electrons may also self-navigate through generated fields. Walking droplets on an oil bath show diffraction patterns when passing through slits, despite being classical objects. It's like a person walking through fog with a flashlight. They move according to how the light they generate reflects from their surroundings. Rather than treating mass, wave behavior, and motion as separate, they may be interconnected outcomes of an electron's internal structure. Self-propulsion could generate the dynamic field needed for wave interactions. The wave-particle duality would then not be a contradiction, but a dual description of a single self-moving entity. This approach offers a path toward unifying classical mechanics, quantum behavior, and field dynamics. It positions particles not as static units, but as active energy-exchanging systems. An electron passing through a magnetic crystal shows changes in both spin and trajectory, indicating intertwined motion and quantum properties. It's like a glowing gyroscope that spins, moves, and emits waves. The structure is complex, but every part expresses the same unified behavior.